Okay, so last time we were just talking about multivariate density estimation and density estimation in general with kernels. And if you have a density estimator, then you also have a classifier if you want to use generative methods, because you can think about your conditional distribution of x given y and just separate out your data for y equaling your different classes. So for example, for binary classification, we think of y as either taking value 0 or 1. That's sort of a canonical way of expressing our binary classification problem. And then we can just separate out the zeros from the ones and then just form a density estimate. We already know that the Bayes rule takes the form of a density ratio, just looking at the ratio of the densities and thresholding that at a certain value, right, for binary classification. And so it's very natural to then just say, well, I'm going to do a density estimate for each of my classes. The issue with that is that then your density estimation can become very difficult in high dimensions, right? So one way that we deal with this is through something called naive Bayes, where we just assume that each distribution is independent from one another. You don't have to use kernel density estimates. That's the most common way of doing it. But in scikit-learn, you'll see that they don't actually have native support for kernel density estimates. They have other parametric density estimators in that case. But the naive Bayes assumption is that you're just going to separately deal with each coordinate of x, conditional on y, and then combine all of them under an independence assumption, effectively. So we have this exercise, which is trying to get you to start to think about what really is gained by making this independence assumption, right? But first, we're asking just how do we know that this kernel here is a valid multivariate kernel for multivariate density estimation? And if you go back to what I required, all I required was that this kernel integrates to 1 if we just let one of these parameters be free, right? And it's obvious just because that this happens to be the case, just because this is the density for a multivariate Gaussian with identity covariance matrix, right? So if we just let this x naught be free and we integrate it out, then we're going to get that this integrates to 1, because this is the density if x1 is the mean, right? This is a valid probability density function for in the x naught. Right? So we can integrate this out. It gives us 1 just if we evaluate what this is. And that's assuming that this is the Euclidean norm. And that's why I wrote a little 2 there. It's very important that it's Euclidean norm. So, so the next question is, suppose you use this kernel to obtain a multivariate density estimate. And this is a more meaty question. And so this produces an f hat. So you just use this to form our f hat. And then the other alternative is to use the naive Bayes assumption, which is just assuming that you can obtain your multivariate density using a product form, so it factorizes into a univariate density for each of the factors. Right? So this is the naive Bayes assumption, and it's assuming independence of each of the coordinates of x. Right? And so this is naive Bayes. How does it compare to the multivariate density estimate up here? And what do we really gain from making the naive Bayes assumption? If they're different at all. So how can we know whether these produce something really different? And the reason why I brought this up is that this kernel is the PDF for independent Gaussians. If you can write this out in a factorized form. But the kernel being the PDF, the probability density function for independent Gaussians, does not mean that the multivariate density estimate that you get from this is going to be a factorized density. It certainly won't. And so we can see an example of that if we look at the boxcar kernel. Okay. So like I said before, this is a Gaussian PDF with mean x1 and variance I, so it integrates to 1 for part 1. Part 2, they're not the same. So if we just look at what happens if we form the kernel density estimate, and I'm just going to ignore the constant factor in the kernel. So we have this 1 over n, sum over I. This is the average of the kernels evaluated at each data point. So we're talking about what is the density at x prime? Well, we look at each of the j's, compare it to the j's coordinate of xi, square this difference, and then we get this. This is what our multivariate kernel gives us, right? So you have the sum over j of these squared terms for each of the coordinates here. Now, if we compare that to what naive Bayes gives us, for naive Bayes, we do this kernel estimate inside of this product over j's. And so we have the product over j's, then we have the average over i's, and then we have it done coordinate by coordinate, right? So, so these two are not necessarily the same. You could imagine pulling this sum of the j's, turn it into a product of the j. The average over the i's times the product over the j's is not the same as the product over the j's times the average over the i's. So these are very different. And if we think about the boxcar kernel in p dimensions, if we think about the kernel between x prime and xi prime, well, the kernel in the boxcar case is just 1 if this norm is less than or equal to 1, right? And in both of these cases, I'm using a bandwidth parameter of 1. So this kernel is non-zero if and only if the 2 norm between these two is less than or equal to 1. Where if we applied the boxcar kernel to each of the dimensions separately, then we would have that the kernel for that one coordinate, the jth coordinate, is non-zero if and only if the absolute value between xj prime and xij is less than or equal to 1, right? So we can think about when does xi contribute something to the density estimate, right? When is it non-zero, and when does xi contribute something? So in the multivariate case, that's when the 2 norm is less than or equal to 1 between xi and x prime. Whereas for the naive, in the naive Bayes example, it's when this absolute value is less than or equal to 1 for all I, or for all j. So you can think about this. This is this absolute value being less than or equal to 1 for all j. This implies. This is implied by the absolute value, or by the 2 norm being less than or equal to 1, right? Because the 2 norm is lower bounded by this absolute value, right? And so one of these is implied by the other, and so the naive Bayes is going to be not equal to 0 more often. At least in every case that the multivariate kernel density estimate is non-zero, you also have that the naive Bayes estimate is non-zero. So you have that the naive Bayes estimator sort of has a larger window of influence between x prime and xi. And you can see that this forms a box constraint, whereas in the higher dimensional multivariate kernel, you have this ball constraint. And balls and boxes become very different things in high dimensions. Something maybe you know, or maybe you'll see in a different course. Okay, so that's the answer to that question. The Gaussian generative models. So in this case, what if we, instead of assuming that we're going to use a multivariate density estimate, a non-parametric density estimate, sorry, but instead we're going to assume it has a certain parametric form. So the advantage of this is that because we're fitting a parametric form, we can hope to get good properties when the model actually holds, when it's a reasonable surrogate for what's actually happening in reality, because we're fitting a limited number of parameters. It also, you can imagine that this method might have better asymptotic, lower computational complexity when you're going to predict. So that's another advantage to parametric methods in general. For example, linear regression has very fast predict. And so this also can have very fast predict methods. Okay, so in Gaussian generative models, the basic idea is we're still going to model x given y. So we're going to separate out the different classes, the data into its different classes, but then we're going to fit a Gaussian distribution to each of the classes. So the Gaussian distribution is parameterized by its mean and its variance, and these are high-dimensional objects, right? If X is p-dimensional, then its mean is a p-dimensional vector. Its covariance is a p by p matrix. And the only constraint on the covariance matrix is that it's positive semi-definite or positive definite. Okay, so here's a little drawing of what we're talking about. So for each of these distributions, so say the 0 distribution and the 1 distribution, so the red is 0 and the blue is 1, they each could have a mean, which is depicted by these points here, and those are the points at which the density is highest for that class. And then they could also each have a different covariance, a possibly different covariance. So this is a modeling assumption, and it implies certain estimates. So how do we know when one of these exceeds the other? Well, let's think about the level sets of the densities of the Gaussians. So the level sets of the densities of the Gaussians, this is the density of the Gaussian. So this first part is a constant in X, right? So the shape of the level set is not going to be impacted by this constant. Then we have e to the something. So it's a monotonic function of that something. That something is it takes the form of an ellipsoid, and the way that we know that is that it's this quadratic form in X, and it's minimized when X is equal to mu k because this is 0, and this is greater than or equal to 0 because this sigma is positive definite, and so its inverse is positive definite as well. So these level sets are ellipsoids. So we have these ellipsoids, and as we go further away from this mu1, we get smaller and smaller density, and at some point these two meet, and that is that we think of as our boundary of our classifier, because we're going to ask when does one of these densities exceed the other by a certain amount. So linear discriminant analysis is the situation in which we just assume that these covariates are the same. Those covariances are the same between the different classes, right? So here I depicted it where there was a different shape to these ellipsoids. Instead, what if we assume that they have the same shape, because the shape of these ellipsoids is determined by this covariance matrix here. You can imagine if this covariance matrix is assumed to be the identity, then these are just balls. Okay, so LDA, we're just going to assume that sigma 1 is equal to sigma naught is equal to sigma. Right? So it turns out that if we look at the likelihood ratio classifier, what that is we're asking, is F1 divided by F naught exceeding some tau? Well, because they have the same covariance matrix, these constants in front are the same. And so we just have that F1 over F naught is this e to the something divided by e to the something for 1 and for 0 respectively. But then we can pull what's in this exponent together, and so it becomes the difference between these quadratic forms is what becomes the relevant quantity. So that's equivalent to saying, well, is the difference between these two less than some k, or some kappa, right? And so if you look at this sigma inverse, these are the same matrices in this difference, and we have some terms that are going to be the same. We have this x transpose sigma inverse x, and that's the same as what we're going to extract from here. We have some things that are constants. We have mu1 transpose sigma inverse mu1. That's a constant, and the same with mu naught. So we just have the cross terms that are going to be the only relevant factor, and those cross terms look like x transpose sigma inverse mu1 minus x transpose sigma inverse mu naught exceeding some other constant, kappa prime. And that kappa prime is going to depend on the mu naughts and the sigmas, but that doesn't really matter because we're going to end up tuning this kappa prime anyway. And so this indicator that x transpose beta, or we could think about tuning kappa prime, or we can think about Or we can think about actually setting it and finding what it should be. But either way, it's just some number based off of these parameters, which we're going to estimate anyway. And if you think about what this is, well, we can group the sigma inverse mu1 with the sigma inverse mu naught and just call it beta, the difference between these beta. And then this boundary, this classifier, just looks like an X transpose beta exceeding some kappa prime. So this actually turns out to be a linear classifier in the sense that to determine whether we're going to predict class 1 or class 0, all we have to do is look at X transpose times some beta. Look at some linear function of X. And this beta is equal to the sigma inverse times mu1 minus mu2. So what this looks like in 2 dimensions is that there's some line. The beta is normal to this line, and it's pointing in the direction of the class 1. So these, when we assume, what we've learned is that when we assume that sigma is the same between class 1 and class 0, then that likelihood ratio classifier turns out to be a linear classifier in the sense that we're just looking for a line that that determines which class we're going to predict. Okay. So how do we fit LDA? So what we do in this case is just use the maximum likelihood estimates for each of these parameters, and what those maximum likelihood estimates end up being are just the Gaussian MLEs. So these are the empirical mean. So if we just look at the each of the coordinates of, or sorry, we look at each of the x's and we take the mean of those vectors. If this omega sub k is equal to all of the i's such that it's in the k's class, so that's the indices for the k's class, then this x bar sub k is our estimate of the mean, right? This is a vector, x bar, because all of these x's are vectors here. And then we have sigma hat is going to be a pooled variance estimate. And so if you're accustomed to, say, t-tests with pooled variance estimates, then this should look familiar to you. This is our pooled variance estimate. It's 1 over n minus 2, the sum over k, sum over I in this omega sub k. So this 2 is because there's 2 degrees of freedom taken up by the mean estimates here. And you would, in general, increase this if you had more classes than binary. So this would be your estimate of sigma hat. Right? And then your beta hat is equal to the sigma hat inverse times x1 bar minus x0 bar. Right? So this is just plugging in what we had before. Okay, so good things about this. So first of all, because we assume this pooled variance, then this variance estimate hopefully is going to be pretty good in the sense that we're using a lot of data to estimate it. And that's only if you have more samples than dimensions, significantly more samples than dimensions. The downside is that it only fits linear boundaries. So usually we call this the capacitance, the capacity of our learner. What is the, so the question is, what sort of boundaries can we learn? So there's a lot of types of hypothesis classes that we won't actually be able to learn. So we won't be able to learn, say, for example, if all the ones were in a circle or in a ball around the origin and all of the zeros were outside of this ball, we wouldn't be able to learn a class that would separate that. We would have to have a nonlinear classifier to do that. This is a linear classifier. So that's restrictive. And so that's a bit of a problem. So one easy fix is to, instead of assuming that sigma 1 is equal to sigma 2, just let them not be equal. We know how to estimate covariances, and so we can we could estimate them separately instead of having a pooled estimate. Now the story is a little more complicated here. If we think about our classifier, our y hat is going to be the indicator that this quadratic form here minus the other quadratic form for the 0 class is less than some kappa, just like before. But now we won't be able to do all the same cancellations as before. we have this first term is going to be different. We have the x transpose sigma inverse, sigma 1 inverse times x, minus x transpose sigma not inverse times x. And so these are going to be different, right? And so they don't cancel out anymore. You still have the constant term at the end, and the constant term could get absorbed into the kappa. But what this ends up being, because these are two quadratics, it turns out that the boundary that results is quadratic as well. So this is sort of the image that should be in your mind. You have these ellipsoids of various sizes, you have another ellipsoid, and they're different shapes, and then the boundary, the classification boundary, is a quadratic. And that's why we call it quadratic discriminant analysis. And the way we fit this sigma k is just we do it individually. So instead of a pooled estimate, we do individual estimates. Okay. So the nice thing is that this is going to have a higher capacity. It learns more. It can learn a larger hypothesis class. Before we had just lines, and here lines are included in the possible hypotheses that we have, but also we have, in higher generality, we have quadratics. Unfortunately, we have to fit more parameters. So you can imagine that the hardness in the previous, in LDA, was estimating sigma hat. That's where most of the parameters lie. Now we've at least doubled the number of such parameters. Just like with LDA, we have to invert this sigma hat. That's one issue with this. And this generally is not going to be invertible in high dimensions. But this is a problem with all of the discriminant analyses that we're going to be doing, is that you have to be able to invert this to get closed expressions of the decision boundary as before. And there are more modern ways of getting around this. Typically, we assume structural assumptions about the covariance. Okay, so for the rest of this lecture, we're going to be talking about the bank data. And so we'll come back to this in a little bit. So I'm not going to end this recording with an exercise. We're going to conclude with an exercise at the end of the next part. So join me for the next installment.